in the crime to a bullet that was fired from a suspect's gun. And you want to know if they both were fired from the same gun. So you want to compare the two bullets. Or you want to take fibers that was in a room and fibers that were found on the victim of a crime to know if the victim of the crime was done in that room and possibly later moved, or who knows. In any event, this will give more information when you compare two samples. That is the comparison microscope, also very heavily used in forensic analysis. So that is what we have here. This is both stereoscopic and also, as we said here, a comparison microscope. You can actually get a view. I mean, what you probably see through here is like half the screen is the view over here and half the screen is the view over here. And you can adjust all kinds of things to move them closer together so you can compare them more closely. In any event, you see here the comparison microscope. Part of what you're going to be looking at is this sample, and the other part you're going to look at is this one, and you can compare the two based on what you see in here. And of course, when it's all magnified, you can tell, let's say, tiny scratches in here and compare them to tiny scratches in there and see, well, maybe they're from the same piece. Or maybe you could just look at the very edge of this, see if it matches up the very edge of that, and see if the pieces are actually one and the same, or they're completely different. Many things you can learn from it. Just a little bit of a little bit more of an idea about how this works. You have little adjustments over here, so you can actually turn this around so you can get a different view. If this would be a bullet, you can actually turn it around and around and around, so you can get a view of all sides of the bullet. Same thing over here. If this would be one, you can turn it around and around on the stage. You can move back and forth and forward and back, right and left, even up and down, depending on how well the stage has been assembled. In any event, and there are many other settings for this particular microscope, but this is a typical comparison microscope. Here, by the way, is a light. If you want to shine light on it, you have this light. There's also a little connector over here. This would lead not just to, let's say, something visual. It might be able to give signals to a computer, or to save them as a digital pictures. Again, this is a relatively useful and advanced comparison microscope, which is also stereoscopic. In any event, just the main point that you should see is how this is a comparison microscope. We have these two stages for the two samples, and it's stereoscopic because you're looking at it through both eyes. There's a polarizing microscope. We're not going to deal too much with this, but you should know that light can be polarized. I'd rather not explain what that is. It does, getting deep enough into it, this might be, very complex and complicated. But just to understand that there's a certain light that can be polarized and certain samples that will change or rotate the polarization of light that goes through them. And this is very, very important when you're dealing with, let's say, carpet fibers or other fibers that we can say that even though we look at them through the microscope, we can say, well, the color is very much the same. But then again, the fact that two carpet fibers are the same color doesn't mean they came from the same room. However, if you not only see the color, but you also see the way that it changes the polarization of the light that you could see through the microscope, you can send the polarized light through the fiber and see how it rotates this polarized light. You can tell, and they both rotate the same exact degree. Let's say they're both 5 degrees. They both rotate this polarized light 5 degrees. Then you can be pretty certain that these fibers are from the same, let's say, batch, from the same carpet. So you can connect two things in that way. Now, they're carpet fibers. You can't just put the whole thing in a beaker. You have to use a microscope because they're really tiny. So you need a microscope, and you need what they call a polarizing microscope, which analyzes how polarized light gets rotated when it gets through a certain small thing like a fiber. So that is just another bit of information you can get, another kind of microscope that they use in forensic analysis. In order to understand more about other things that these microscopes can do, you have to understand a little bit more about the nature of light. Now, you may know this, that light is basically an electromagnetic wave, which is an oscillating electromagnetic field vector, but we'll call it a wave for our own, to make it simple. All light and energy and electromagnetic energy is in the form of waves. It's particles also, but we're looking at the wave aspect of it. They are different. They differentiate. They're different from each other by their frequency. The high energy light, we're not talking about high intensity, but higher energy in the forms of, let's say, gamma rays or X-rays. I mean, these are the dangerous ones. Ultraviolet rays, these can be dangerous to living matter. They're dangerous because they're very high energy. They can actually, disrupt the atoms that the organic molecules are made of. So that's high energy. They have short wavelength and high frequency. The idea is the frequency, let's say, we'll call this like in one time period over here. In one of these, let's say 1 second, whatever it might be. This one time period, we see that there are three waves hitting you. This one, but because they're short wavelength. In the same time frame over here, you'd only get one wave hitting you. So that's a lot less energy. So we can see how the short wavelength over here leads to high frequency and therefore high energy, whereas the long wavelength over here leads to low frequency. Again, it's only one of them hitting you because it's so long, and therefore low energy. The low energy ones are like the radio waves over here. Radio waves are completely and totally harmless to organic matter. As we speak, there are radio waves passing right through us all the time from your local radio station. They're just getting right through us and harmlessly, and they've been doing it our whole lives. They are, again, very low energy, not enough energy to disturb any of our organic matter, so therefore they're fine. You don't want to have radio frequencies sending a broadcasting short wavelength. That'll, kill a lot of, living things. So short wavelength, high energy, high frequency. Long wavelength, that's the easygoing, low energy, and low frequency radio waves. Now, in between the two, we have here visible light. Now, visible light is composed of different colors. Now, what we see as white light is actually a combination of all the colors of the rainbow. And you can see this. If you put a prism in the white light, it'll actually divide it up into all the colors of the rainbow because these different colors have different frequencies. Here, the blue ones have the higher frequency, and the red ones have the lower frequency. Blue ones have the shortest wavelength, high frequency, high energy. The red ones have the the long wavelength, low energy, low frequency. So that's where the visible light, and you can see from the electromagnetic spectrum, it takes up a very small piece of it. Nevertheless, we use it to see the world around us. Of note that the higher energy, higher than the blue, is what we call ultraviolet. Now, our eyes can't pick it up, but it's around. Same thing, the lower energy than the red is called infrared. We can't see it. Certain animals can. I believe the mantis shrimp can actually see infrared and ultraviolet. They can, believe it or not, I think they can also detect the polarization of light. But anyway, the light we have, again, the higher energy is the ultraviolet, lower energy is infrared, and we see this narrow band of visible light. So our light is composed of a mixture of all different kinds of colors. We can actually, let's say, block all